sorts of things. Today is the 10th, correct? 18. Ah. Okay, so we're going to talk about forces and laws of motion, and all force is, it's really pretty simple. It's an object interacting with its environment. Forces tend to cause accelerations, and a lot of you correctly identified that when we're talking about gravity, that gravity is a force and it tends to cause objects to accelerate. You even know the rate at which it tends to cause objects to accelerate. So let's look at my little friends here. We've got the little Newton's cradle here, and I want to ask you a couple of questions. So, at this point, it's not moving. I'm going to lift one of these spherical objects, and I'm going to let go. What causes it to move when I let go? Gravity. Gravity, yeah. Now, something odd will happen. Whoa, it's so cool. It's entrancing. You could look at it all day. This is why I encourage you to build a life-size one outside your house maybe, or in your dorm hall. And you can probably charge people admission. What's causing the other balls to move? Transfer of energy. They hit one another, and they exert a force on the next object. So what that leads us to is the fact that there are two kinds of forces in this crazy mixed up world of ours. Oh, shoot. I guess we should talk about measuring first. We can measure those forces on those little tiny spherical objects. We can measure the forces on your collarbone when you fall. We can measure the forces on the paperclip when you throw it. Don't throw them right now. And we're going to measure those in newtons. So newtons are the SI units for force. They are a derived unit. And 1 newton is equal to 1 kilogram of mass being accelerated at 1 meter per second squared. Now, most of you, a lot of you actually referenced F equals ma. And even if you didn't reference it, I suspect that you remember it from somewhere in the recesses of physical science. It's been a few years, I know. But if we take F equals ma, and we look at that dimensionally to do the dimensional analysis on it, we're saying that 1 newton equals 1 kilogram times 1 meter per second squared. And we just said that 1 newton equals 1 kilogram meter per second squared. Hey, that's cool. It works out. When you are doing larger, more complicated rearrangements using forces, it's handy to have that in your back pocket. The way we typically write this for newtons is we'll say it's 1 kilogram meter per second squared. If you're doing that. And I think the front of your book has got the dimensional analysis for common units, so when we get to joules and energy, you'll see those too. Okay, cool. Here's the setup. So, we took a spherical object, we lifted it, you say gravity made it move down. Yes. But then it starts a chain reaction, well, not really, anyway. It hits the next object, it exerts a force on it. So there are two kinds of forces, and we just showed them both. One is a contact force. And if you take the paper clip that's on your table, any of them, did I actually finally give everybody a paper clip? Set it on the table and exert a contact force on it. Yeah, you're physically touching it. You're moving it. You have to be in contact to exert a contact force. I know that's completely counterintuitive, isn't it? Versus a field force. So when we're talking about, do you still not have a paper clip?
Oh, no, I do.
Oh, okay, good. I was worried there for a second. Versus a field force where you don't have to touch it. So name me another field force besides gravity. See if I can separate these. Woo, sorry. Magnetism. Magnets. They're fun. Magnets. You guys have the rare earth one. So, field forces have a region of influence, essentially. And if we are looking at the Earth, if that's the surface of the Earth, how far out from the center of the Earth does the field of gravity extend? Where's the end of basically Earth's gravitational field? It's really far out there. So the moon, why is the moon orbiting us? Gravity. Because the Earth is so darn attractive. The moon is held in place by the gravity of the Earth. So the field of influence of that field force of gravity extends out to the moon. We often, you sometimes see references that the extent of Earth's gravitational field is basically top of atmosphere. What's holding our atmosphere in place? What's the atmosphere made of? Talk amongst yourselves. Talk at your table. What is the atmosphere made of? What's holding it in place? Gases! Which are made of molecules. Do they have mass?
Yes.
Yes. In chemistry, we do the masses of gases. And you can finish that thought any way you'd like. Those gases are acted upon by gravity. Each of those individual molecules is being attracted to the center of the Earth. Whoa! The outer extent of the outer extent of the point where Earth's gravitational field is strong enough to attract little teeny tiny particles is top of the atmosphere. Now, the gravitational pull extends beyond that because it's able to attract a large object like the moon, but there comes a point when it has to be a pretty large object for it to be attracted. That magnet that I gave you on your desk, stronger or weaker than the Earth's gravitational pull? Talk about it amongst yourselves. So not all field forces are created equal. We're actually not really sure why magnetic forces are stronger than gravitational forces. And I'm not enough of a physicist to even get into the details of why, but suffice to say, it's weird. So the field is how far out you can see the influence of a force on other objects. You can test the edge of a magnetic field by seeing the point at which it starts to pull the paperclip. Okay, you were waiting eagerly for this, I know. Force is a vector. Whenever we specify force, we have to specify direction, so magnitude and direction. And just as we've done with every single other vector we've talked about, we have represented accelerations and velocities and displacements with arrows. We represent forces with arrows. If you are going on in physics, if you're doing any form of engineering, you're going to do some different representations than we do here. We do the really simplified diagrams for forces. They're all just arrows. In more advanced physics, the different arrows are sort of coded for different forces, and there are standard sort of codes for it. At this level, it's typically not done that way. But if you're going on, you'll see that it is. So just like any other vector, we show arrows, and we label. So if I am pushing on this thing, this could be the force of Moser, if I am exerting a force on an object. We label if we know the magnitude of the force. We add that. Fairly simple. Okay, so there are two different kinds of ways to diagram forces, and one of them we never use. Force diagrams are very comprehensive. They show every single force in a situation. I want you, for just one moment, to imagine yourself on that chair. There's you. And you've got the floor. And if we want to get really crazy, you have little particles in the air around you, little molecules. Can you identify every force acting on that situation? Every force acting. Okay, are you saying that I should draw this person with their hands not like that? There. Is that better? Hey, I'm doing my best. Can you identify all the forces that are acting in that situation? Give me one. Low-hanging fruit goes to the fast. Come on.
Gravity.
Acting on what?
The chair.
Okay, so we have, and I'm going to color code these, force of gravity acting on the chair. is anything else acting on the chair?
Us. By sitting on it.
Okay, so there's the force of your butt sitting on that chair. Oh, wait, let's see. So that's an additional force on the chair, which kind of adds in with gravity, but okay, we'll accept that. Other forces. Is the chair exerting a force on anything else? Okay, and before anybody takes issue with my artwork, I understand that as drawn exactly, no, because you were magically levitating over the chair, but anything else? Is the chair exerting any forces on you? Yeah. Chair is exerting a force upward on you. What other colors can I do here? Do white. Anything else? Is the floor exerting a force on you? Yeah, if you're touching the floor. So we've got that one. Let's change colors again. I'll go for sort of peachy. Force of the floor. Is the floor exerting a force on the chair? Oh yeah, we got that. That's up, so force of floor. Are the air particles exerting a force on you? Yeah. Okay, you see that this gets completely untenable really fast. It's sheer madness. This way lies insanity. So what we do instead is we do what's called a free body diagram, and a free body diagram isolates a single body in the situation and then just looks at the forces on that body. Much more manageable. So the other thing that we tend to do in free body diagrams is we generalize the shape of the object. We don't usually draw real good anythings. We tend to draw a lot of this, and that is you or the car or the anything else. And I mean, you can do a little bit better than, you know, the simplest box on the planet. And sometimes we've had people who get fairly creative with their free body diagrams, which is fine, but don't lose sight of the fact that the point is really that we're simplifying the object and we're sort of isolating all the forces to that center of mass. Simple process. Draw an object. And we approximate the shape. That is to say, for a free body diagram, that's a reasonable human. Looks like a Weeble people. That's fine. You are a, roughly 1.5 meter cylindrical object in physics. Don't you feel special now? So we draw the object, we position the object accurately. If we've got a human who is in the air, on the ground, we can just do something like that. If we have a box on a hillside, we better do something like that. I should move that up. Because we want to see that there's a slope. So in cases where, and we do sometimes kind of add ground as an I'm trying to think my way through the unconscious assumptions that I am not speaking. We most often show the surface if the surface is not horizontal. So as long as the surface is horizontal, we very often skip showing it. If there is something of note about the surface, like, oh, hey, they're on a slope, we generally show that, if it's a sloped surface. If an object is connected to ropes or strings, we typically show that. And we're going to do a lot of those kind of problems. Those are called force attention problems. So if we have an object that is suspended by two strings, we typically show that. Okay? So we kind of show the minimal amount of stuff we need. Now, when you draw forces, probably the most important thing on this whole page is this right here. Forces are always shown as originating at the center of the object. Are you familiar with the term center of mass? So if we basically average you or any object, we can find the spot that is the center of mass. The lower the center of mass is, typically the more stable you are. Does anybody here backpack? other than me? Okay, never mind. One year I had like 4 backpackers in a physics class. It was fabulous. Because it's a big concept. If you're carrying, you've all carried backpacks on your back. The higher the mass is centered in your backpack, the less stable you are. Now, it also changes which muscles you use to move that pack. But lowering the mass tends to stabilize an object. If you were out duck walking on ice this morning, which I was, keeping your center of mass lower actually stabilizes you. Put bricks on your head, you're less stable. So we're showing all the forces originating out of this object as though they originate at the center of mass, because that's kind of where forces tend to act on you. So we show them all coming out of the center. So for this little person, I'm going to show the force of gravity coming out of the center. There is, obviously, if there wasn't another force acting on them, they would be accelerating downwards towards the center of the Earth. We don't always, but we often do color code forces in free bodies. So I'm going to show the other force that's acting upward on them, which we haven't talked about yet, but we will next week. It's normal force, as coming up that way. If you know the magnitude of the force, you should put that. So if we know that this person has a particular mass, and so the force of gravity on them is 100 newtons, which would be a pretty light person, as long as we know that they are not crashing through the floor or rising up into the air, we know that the normal force on them is also 100 newtons. And if we know those, we label them. We don't always know them. Making sure that forces are shown acting in the correct direction. This is especially important when we get to the slope problems, and we'll do a lot of slope problems. Inclined planes and sloped streets and stuff like that. There's the force of gravity. We're going to talk a lot about gravity versus normal force. Force of gravity is always acting straight down towards the center of the Earth, whether you're on a slope or not. The force that board is exerting upward is perpendicular to the surface of the board. We'll talk much more about that. That is not the only coverage we'll get of that. But whenever you're doing free bodies, you want to make sure that your forces are aligned correctly. Even if you're not a strong visual learner, which some of you are, that just like with vectors, having a good visual helps you understand the problem better. Okay, goes without saying, they're useful. It's almost impossible to do force resolution without free body diagrams. So we're going to practice a couple. We'll do one as a class, and then I'll assign a few and cut you loose and let you work for the last few minutes on those. Okay, I have a box sitting on the ground. Okay, so I've got a box sitting on the ground, 15 Newton force of gravity is acting down on it, and a 15 Newton force is acting up on it. Draw it. Okay, so you should have something that looks like that. The first couple problems I'm going to assign are really just practicing free body diagrams, though I promise they're a little bit more complex and interesting than that one. Okay, page 128, it's actually the section review, numbers 1 through 4. You can get started on.